In this video, we will discuss how to maximize or minimize a function without any constraint. First, we will consider an optimization problem with one explanatory variable, and then we will move on to solve an optimization problem with two explanatory variables. Consider a function with one independent variable. Y is equal to 5x square minus 40x plus 20. So this is equation 1. To determine the extreme value, the maximum or minimum for this particular equation, the first order condition requires dy by dx is equal to 0. Now dy by dx will be equal to ddx of, since y is this, we will replace it 5x square minus 40x plus 20, and this will be equal to, after differentiation, 10x minus 40, using the basic rules for differentiation. Therefore, if we make dy by dx equal to 0, it means that 10x minus 40 is equal to 0, or x is equal to 4. Now to check if the function has a maximum or a minimum at x equal to 4, we find the second derivative. So second derivative is d square y by dx square, or we can write it as d dx of dy dx. Now we already found out dy dx, and that was equal to ddx of dy by dx we found out as 10x minus 40, or after differentiating this we get equal to 10, and 10 is greater than 0. If you recall the condition for maxima or minima that you learned in the previous video, you will conclude that x equal to 4 minimizes the function y is equal to 5x square minus 40x plus 20, because the sufficient condition for a minima is that the second derivative must be greater than 0, and we have the second derivative greater than 0. Let us now consider a function with two independent variables. Suppose z is equal to 3x square minus 12x plus 4xy plus 2y square minus 8y plus 100. So if you look at this equation, you see that we have two independent variables, x and y. To determine the extreme value, the maximum or the minimum in this case, the first order condition will now require partial derivative of z with respect to x, partial derivative of z with respect to y, and both must be equal to 0. So this is the first order condition. And after differentiating, suppose partial derivative of z with respect to x, we replace the value of z with the equation 3x square minus 12x plus 4xy plus 2y square minus 8y plus 100. So after partially differentiating this equation, we will be left out with 6x minus 12 plus 4y. Suppose we mark this as equation 1. And partial differentiation of z with respect to y, we will get partial differentiation of z with respect to y will be equal to 4x plus 4y minus 8. Let us mark this as equation 2. Now simplifying equation 1 and 2. Equation 1 is 6x minus 12 plus 4y is equal to 0, and equation 2 is 4x plus 4y minus 8 equal to 0. We equate it to 0 because the first order condition requires us to equate the partial derivatives to 0. And simplifying these two equations, we get x is equal to 2 and y is equal to 0. In order to check if the function has a maximum or a minimum, we test the second order condition. The sufficient condition for maxima requires h1 less than 0 and h2 greater than 0. And suppose we have a general form up to m, then minus 1 to the power m hm will be greater than 0. This is for a maxima. And for a minima we have h1 greater than 0, h2 also greater than 0, and hm will also be greater than 0. M is the number of explanatory variables in a function. So this is the sufficient condition for a maxima and a minima with two explanatory variables. In our example, if you remember, partial derivative of z with respect to x, we got it as 6x minus 12 plus 4y, which we marked as equation 1, and partial derivative of z with respect to y was 4x plus 4y minus 8, and this was equation 2. Now from concept of Hessian determinant, here h is the Hessian determinant. For our example, h1 is equal to del square z del x square, or we can write this as del x of del z del x, or this is equal to del x of 6x minus 12 plus 4y. Therefore, determinant of h1 gives us 6, which is greater than 0, and determinant h2 will be del square z by del x square, del square z by del x del y, del square z by del y del x, del square z by del y square. You can go back to the e-text and look at the Hessian determinant definition. Using equation 1 and 2, we get del square z del x square is equal to 6, del square z del x del y is equal to 4, del square z del y del x is also equal to 4, and del square z del y square is equal to 4. Therefore, Hessian determinant H2 will be equal to 6, 4, 4, 4, and this determinant is equal to 8, that is greater than 0. Hence, at x equal to 2 and y equal to 0, the function is minimized.